So I'd like to talk to you a little bit about tiles and sort of the mathematical weirdness that you can access with some quite simple tiles. So, tiles, as in, like you could tile your kitchen with these, or a courtyard or something. So nothing magical about them. Some shapes that lock together in a certain way. So I'm going to start out a little bit heavy on the maths, and then hopefully it'll get easier. I'll finish up with a few tiles that I've found myself that are hopefully fairly straightforward to understand. So, I'll link to these slides in the description. So there's various links here if you want to dig further. There are many rabbit holes you can go down to do with tiles, many really interesting stories. So where I'm going to start is with Hao Wang from Bell Labs, who made a conjecture that turned out to be wrong. So Wang was interested in a particular type of tiles, I think mostly to make the problem easier. So think about square tiles with coloured edges, and the rule is where you can put two tiles next to each other if they have the matching coloured edge. And we're not allowed to rotate tiles, and we're not allowed to flip tiles. So, and I think this is mostly just to keep things simple. In terms of the colours, you could just as well have a sort of wobbly edge that would physically limit the tiles to match in various ways. So these really are things that we could build in the real world, and whether we can make a tiling pattern with them or not, that's something we can do in the real world. Now, so Wang had a conjecture. If we can tile the plane, if we can make a pattern as large as we like with no holes in it or mismatching colours, then his conjecture was that we could do it with a repeating pattern. So there's some block that you can sort of lay out a repeating pattern, and so if it's possible to tile the plane, there will be such a block. This turns out to be wrong. So Wang had a student, Robert Berger, who showed this is wrong. And so what that means is there are what are called aperiodic tile sets. You can cover the entire plane with them, but the pattern never repeats. There's no way to make it repeat. So Berger's initial version of this required over 20,000 Wang tiles. Over time, that number has been whittled down. And so we now have a result on the minimum number of tiles you need to force a periodic tile. That turns out to be 11 tiles. So these guys proved the minimum. They proved you can't get any less tiles. So these are their tiles with numbers rather than colours. And then this is a sample arrangement of their tiles. So it's not repeating in any noticeable fashion. So just a bit of a digression maybe. Why were Wang and Berger interested in this? And so beyond tiling the plane, Berger had this slightly more complicated question of, like, is it even decidable whether a set of tiles can tile the plane? And it turns out it's not even decidable sometimes whether a set of tiles will tile the plane. And so the trick here is he gets one of these aperiodic tile sets, and what that does is, so it's relatively straightforward to implement a Turing machine as these Wang tiles. Like you have a particular set of tiles for the head of the Turing machine, and maybe So each row of the tiling will have one head, and it will maybe move left or right, and you can set up your tiles to achieve that. It's an interesting little exercise. And so you could make one of these Turing machines that it's undecidable if it halts or not. So that's sort of importing the halting problem into tile sets. Except there's one problem, and that is sort of like initializing the Turing machine. You have to start with like a blank tape and the head, exactly one head at one position. So the trick Berger used was these aperiodic tiles, and the particular aperiodic tile set he used, he could sort of identify a starting point within that would sort of overlay the Turing machine on these tiles, and at places scattered throughout the tiling, the Turing machine would run for some number of iterations within a little area, and in fact, for any number of iterations you want, somewhere within the tiling, the Turing machine will run for that many iterations. And that's enough to like transfer the results from Turing machines to Wang tiles and say that it's undecidable in some cases whether a tiling set can actually cover the plane or not. Okay, that's a bit of a digression, going a little bit deep for what I'm wanting to talk about here. So with these square tiles and the limitations like not being able to rotate them, you can get it down to 11 tiles. If you allow rotations and flips, I think you can get it down to like 6 square tiles. But then if you give up on square tiles and allow any shaped tiles, it's possible to get it down to 2. So this is a famous discovery by Roger Penrose. So he was sort of, the way you get to this is you sort of try to tile the plane with pentagons. This does not work. There's always gaps if you try to do it. And then Penrose sort of filled in the gaps in various ways and found he had a small set of tiles, 6 initially, that could tile the plane, and turned out to tile it aperiodically. Some further fiddling around reduces this down to 2 tiles. There's various pairs of tiles that do this. There's a kite and dart form that was sort of initially quite popular. Probably the simplest one is this sort of 2 rhombus tiles form. So there's a thin rhombus and a thick rhombus, and then along the edges we have some rules of how they'll match up. So what I'm doing here is I've got sort of jigsaw puzzle notches and dents that force them to match up in a certain way. Another popular way is like you could have some decoration on the tiles, like stripes, and then the stripes have to match up. So this is actually a building in the RMIT University Story Hall. It's sort of decorated inside and outside with these. These things have been used as architectural decorations in a few different places. So if we were doing this talk in person, I would give you a bucket of tiles and let you have a chance to actually assemble them. You can sort of, it is possible to cover as large an area as you like, but you sort of sometimes realize you've made a mistake and you might have to backtrack, or even backtrack arbitrarily far. So it's sort of fun to play with these. And I'm thinking it'll be fun to give people a chance to actually do that, but over the web we can't do that at the moment. So, okay, here's one I made up myself earlier. I got some foam sheets and a cutting machine to cut out pieces from foam sheets, and then I've assembled them on my living room floor, as you can see, and it makes quite an attractive looking pattern, I think. And yeah, this can be extended indefinitely, but without ever repeating. So that's 2 tiles. Oh yes, there's more to say about Penrose tiles. So, like in terms of this non-repeating pattern, it's non-repeating, non-periodic, but it's a relatively straightforward method to cover the plane. Starting with a small arrangement of these tiles, what you can do is enlarge them by, turns out, the golden ratio. The golden ratio is somehow related to pentagons. So golden ratio pops up a lot talking about Penrose tiles. So anyway, you have an arrangement of tiles, enlarge them by a factor of the golden ratio, and then there's some substitution rules. I nicked these from the Tiling Encyclopedia website. But it's edge matching rules by these orange bands. Anyway, so any tiles in your original tiling you replace with this. Some of them sort of slop over the edges. Hopefully the matching tiles say also put this tile here. And once you've done that enlargement, you do the enlargement again and again as many times as you like. So there's this sort of hierarchical pattern that the Penrose tiles forms, aperiodic, but not all that complicated. So that's one way of laying out Penrose tiles. There are other ways. So apparently it's possible to sort of look at a collection of cubes in a higher dimensional space and projecting them down to 2-dimensional space in a particular way produces a Penrose tiling. There's also a way to decorate these tiles with Aman bars. And then those bars form straight lines, so various sets of parallel straight lines. So parallel, but the spacing between them is sort of aperiodic, and that's a whole other rabbit hole into some sort of mathematical number theory sort of stuff. So yeah, really some quite interesting mathematics that can be applied to these. So Penrose tiles have had quite an impact on the world, I think it's safe to say. So Penrose, we're sort of going from the mundane to the less mundane here. Penrose actually patented his tiles. I'm not sure we should necessarily approve of that, but that's what he did. And I think the reason he did that was he was developing a sort of a toy puzzle that I think that was then like manufactured, and you could buy this puzzle. The way he did that was taking the kites and darts form of Penrose tiles and turning them into sort of chicken-shaped pieces. So his prototype of this has been carefully stored in the British Museum collection for future generations to look at. And if you look online for auction sites, you might be able to find the finished product. Okay. Penrose tiles have also been used as like a motif in various bits of architecture. In my home city of Melbourne, there's RMIT's Story Hall. So that's this building I was showing here. There's some speculation that something like Penrose tiles was used in Islamic architecture in the Middle Ages. I'm not sure I quite believe that, but there do seem to be some links. And yeah, it's sort of maybe anyone who plays around with pentagons enough, they come up with something like these. So it's not impossible. And then sort of the real shocker, crystals or quasi-crystals following these like aperiodic patterns turn out to actually exist. So for a long time it was believed, like, well, I mean, still is true that if you have a regular crystal structure, the rotational symmetries are limited. So things like 5-fold symmetry, rotational symmetry, or 10-fold rotational symmetry are forbidden. You can't lay out a regular lattice of atoms like that. And so I think people saw this in like these diffraction patterns and but knew it was impossible, and so didn't pay attention to it. Eventually a guy called Dan Shechtman insisted on talking about it enough that people realized what was actually going on. He got a Nobel Prize for that. And so, yeah, initial examples of this were funny crystals created in labs under unusual conditions. But then it was found, like, a quasi-crystal was actually found in nature. It was found in a meteorite. So it was quite an adventure story to go with this. This is a video by a guy called Paul Steinhardt. So his research group found a quasi-crystal in a collection of mineral samples, and then so he had this one tiny speck of quasi-crystal, and so he wanted some replicates of that to prove it's like really real. So he found the guy who discovered it in the first place, and they went on this expedition to far eastern Russia and found some more of them. So these things really do exist in nature, in meteorites at least. Okay, so that's Penrose tiles. We got it down to 2 tiles. Can we get it down to 1 tile? Well, kind of. So looking at this here, each of these colors is a tile, and each of them is the same shaped tile. And yep, this one tile does tile the plane aperiodically if you allow rotations and mirroring. But yeah, you'll notice like it's not a connected tile, so it feels like a bit of a cheat, but this is as good as we can get probably with a single tile that tiles the plane aperiodically. So this is the shape form of it. You can also decorate tiles, and then there's some slightly complicated rules that also lead to also like produce the same tiling pattern. Forms this nesting triangle pattern. It's quite attractive. So these were found by an amateur mathematician from Tasmania, Joan Taylor. Then I think what happened is she contacted the Cellular guy, and they developed the theory of it. So this is probably as simple as we can go with aperiodic tiles. Okay. So I'd like to move on now to, we've been forcing aperiodicity just with the set of tiles. I'd like to look at some slightly easier problems. If we allow further rules on how the tiles are going to be laid out, it's really easy to force aperiodic patterns. But I don't know. I just like tiles as an really physical way of getting at mathematical ideas. So I have a couple of examples of that I'd like to talk about. So starting with my favorite tile that I found one day. So, well, there's this interior tile, and then I'm going to add 3 of these corner tiles. And what I'm going to do is make the rules here. You use 3 of these corner tiles and as many of these interior tiles as you want. and like making sure all those jigsaw protrusions have matched with a hole like that. So what sorts of patterns can we make with this? Let's start with the 3 corner tiles. They lock together like this, so this is sort of the smallest pattern that matches the rules I'm setting here. We can make it a bit more complex, adding these interior tiles. Then go a little more complex. It's got a hole in it. I'm going to say this sort of hole is acceptable in a tile layout like this. That's odd. I mean, it sort of looked like it was just going to make a big triangle, but no, it's a triangle with a hole in it now. If we go a further couple of steps, maybe you can start to see the general pattern here. Still using the same tiles, we have a sort of Sierpinski Triangle pattern emerging. Okay. Extend that as far as we like. So if this were an in-person session, I would have sort of brought out a big bucket of these tiles. I've got enough here to do like one further step larger, but I don't have enough floor space at home at the moment. And like we could actually construct one of these. But I can't do that online, unfortunately. So what's going on here? So here's one explanation. There's an underlying hexagonal pattern. And then these interior tiles you can view as sort of an XOR cellular automaton. So a one-dimensional cellular automaton. We have rows of tiles, and then there'll be some rule for how you color a tile based on the tiles above it. Turns out these tiles effectively do an XOR, like the XOR of exclusive OR of the two colors above it. So if either one is like red, but not both, then it'll be red. Or it'll have an output of 1. And it also sort of tells its neighbor what color the tile above is, but that all matches up. So effectively this is an XOR cellular automaton. And then this automaton seeded with a single on tile forms this Sierpinski pattern. So requiring these 3 corner tiles is enough to force it to be that Sierpinski pattern. So cellular automatons are kind of interesting. So a guy called Stephen Wolfram was in charge of writing Mathematica. He wrote this big book, A New Kind of Science. It's quite a big, thick book, but it does have a few interesting ideas in it, I think, that do hold up. And so one of the things he did in this with his collaborators was look at what he called all of the elementary cellular automata. You can think of these as a class of simple computer programs. And it turns out there are exactly 256 of them, so it was possible to look at all of them. And sort of one of the theses of this book is that simple programs produce great complexity. So several examples of this were found. So 90th elementary cellular automaton produces the XOR pattern I was just showing. The 30th one is kind of weird. It produces a pseudo-random pattern. And then the 110th one with a sort of suitably contrived starting row turns out to be like Turing complete, you can implement a Turing machine with it. So this idea of just surveying all the simple programs, that's sort of what inspired me to go looking for simple tiles, which is how I found my favorite tile back there. So this rule 30 is kind of interesting, so let's look at that a bit. So the way these work, we'll initialize it with like a row like this with one square that's on, and then there's a rule for producing each subsequent row. So each square, the color is determined by the 3 squares above it. So there are 8 possibilities for that, each with a choice of 2 colors. And that's how we get to 256 of these elementary cellular automata. So this is rule 30. We convert that to binary, and that determines the colors of the outputs here. And that produces this pattern, which is like, so for example, if you take this column here and keep extending the pattern, this produces really high quality, like pseudo-random numbers. I think Mathematica used this as its random number generator for a few years. I'm not sure if it still does, but at least initially I think it did. So, well, that's a sort of interesting mathematical thing, but what if we could make this like exist in the real world? What if we could make some tile pieces that like physically like just insist that they're going to make exactly this weird pseudo-random pattern and no other pattern? Well, we can do that. And so sort of the trick here, like these tiles are representing the outputs for these various patterns, and like the problem is sort of looking up and to the left or up and to the right. And so the trick is that each of these squares is going to tell its neighbors what the color is of its own squares. So it looks up to its neighbor above, and then it tells its neighbors to the left and right what color it saw. And so if it's like black above, it'll have protrusions here and here. And so with that, each tile knows these 3 colors, and then it can decide, does it have an output? Like, is it itself a black tile? If so, it'll have a protrusion, otherwise it'll have a flat piece. And then to start it off, I'll have a single big bang tile, start with this piece, and then extend the pile outward. Extend the tiling outward from this is going to be the rule. And so I cut out a bunch of these tiles, and if you tilt your head, you can see this is the same as that rule 30 pattern. If I got out my bucket of pieces and assembled this again, it would produce exactly the same pattern. So if this was in person, I'd give you a chance to have a play around with this. So, but unfortunately, we can't do that. And then I guess one final thing to note about this, like this Big Bang piece is like it's a slightly awkward extra rule we needed to do this, but like that trick Berger got up to with his aperiodic tiles, that he's got an aperiodic tiling, and within it, he used that to sort of have runs of a Turing machine for however many iterations you want somewhere within it. We could do the same exact thing with these rule 30 tiles. You could have an aperiodic tile that contains within it runs of the rule 30 for as long as you like, somewhere within it. So this need for a big bang that needs a special rule different from the sort of local rules implied by the tile shapes. It's possible to get rid of that requirement. So anyway, so I don't know, just kind of find it neat that sort of mathematical thing we can do can actually create it as a physical object that insists on producing this particular pattern. So that's my presentation. I guess I'll finish by saying, well, I started by saying we can access mathematical weirdness using tiles of various shapes, but these are fairly simple things. They are physically real things. You can hold them in your hand. So this is more or less Wolfram's point that maybe this sort of mathematical weirdness is actually normal. Sort of, we don't run into it because we tend to avoid it rather than because it's actually unusual. So anyway, I hope you found that interesting. Thanks for listening.